Hi there, Mr. Sutton here, bringing you the AB Calculus 5-8 Extra Practice number 3 solutions on FTC derivatives of integrals. For this problem, we're trying to take the derivative of this integral right here. Since we have a variable in the upper limit of integration, we're going to use our FTC. So basically, we're going to plug this x squared in for the t in the integrand, and we're also going to have to use the chain rule in a second. But let's do the outer function first. So we're just going to have 2x squared minus 1. But now we're going to have to multiply by the derivative of x squared, which is 2x. So this is the chain rule in action. And if you wanted to, you could simplify this to, this would be 4x cubed minus 2x. To take the derivative of this integral, since we have a variable in the upper limit, we're just going to use our FTC and plug in this x for the t in the integrand. So this is just 3e to the x. And that's it. On this problem, we're given this g function, which is the integral from 3 to x of this polynomial, and we want the x-coordinate of the point of inflection for the graph of g. Well, if I want to know where g has a point of inflection, I need to know where g double prime changes sign. So it'd be nice if I knew where g double prime had a value of 0. That would be a good starting point. First, I need to get g double prime, though. So let's start with just g prime. G prime, using my Fundamental Theorem of Calculus, is just going to be all the stuff in the integrand here with this x in the upper limit of integration plugged in for it. So g prime is just going to be x squared minus 5x minus 14. And then g double prime, just using the power rule, is going to be 2x minus 5. So let's see where this equals 0, and then we'll do some sign analysis. So if I add 5 and divide by 2, we have a critical value at 5/2. Doing some sign analysis around that, and I'll just plug things into g double prime here. So let's test something less than 5/2, like 0. That's just going to be 0 minus 5, which is negative. Something bigger than 5/2 would be like 3. So this would be 6 minus 5, which is a positive. Since g double prime changes sign at x equals 5/2, g therefore has a point of inflection at this x value. So that's going to be choice B. For this problem, we're just trying to take the derivative with respect to x of this integral. Now, the trick on this one is recognizing that we have this variable in our upper limit of integration. So this is a situation where you can just use your Fundamental Theorem of Calculus and replace the dummy variable with whatever is in this upper limit. This is just going to be sine of x to the 4th. And we would multiply by the derivative of x, but that's just 1. So this is going to just be our final answer, choice A. On this problem, we're given this graph of f, and we're told that h is the integral from 0 to x of the f function. So we want to know what h prime of 4 is. Well, to know what h prime of 4 is, it'd be nice if I knew what h prime of x was in general. Since h is just this integral function, taking the derivative of h really just means using our Fundamental Theorem of Calculus over here and replacing the t in here with the x and getting rid of the integral. So this is just going to be h prime of x is just going to equal f of x then. And that means that h prime of 4 is really just f of 4. Well, what's f of 4? We can look that up in our graph. At the x value 4, the f function has an output up here of 5. So that's our answer, choice B. For this problem, I'm given this h function, which is an integral with a variable in the upper limit of integration, and I want to know what h prime of x looks like. So for this, since I'm taking the derivative of one of these types of integrals with this variable up here, I'm just going to use my FTC. So I'm going to start by replacing the dummy variable t with whatever's in this upper limit of integration. So I'm going to write square root of 2 plus x cubed squared. But since I have an x cubed up here, it's really more than just an x. I have to actually apply my chain rule and multiply by the derivative of x cubed, which is going to be 3x squared. And then if I clean this up a little bit, I can move that 3x squared out front, and I can write this as 2 plus x to the 6th. So that's going to end up being answer choice D. On this problem, we're given some selected values of h and its derivative in this table. And we're also told the f function is the integral of the h function from 0 to x. we want the least number of possible critical points for f on the interval from 2 to 13. If I'm looking for critical points for f, I'm basically asking, where does f prime equal 0 or undefined? Now, since f is based on the h function, and they told us the h function is differentiable, most likely we're not going to find any place where f is undefined, so or even f prime. So really, we're just looking for places where f prime equals 0. Well, we don't really know what f prime looks like yet. Let's go ahead and take the derivative of f, because it's defined right here. So f prime is going to be the derivative of this integral. Now, since this integral has a variable in the upper limit, we can use our fundamental theorem of calculus and just replace the t with this upper limit of integration. So this is just going to be h of x, and that is going to be equivalent to f prime. Since f prime is really just h, that means we're asking, how many places does h take on a value of 0 between 2 and 13? And for that, we have a little bit more guidance because we have this table of values for h. Now, the key is, because, we don't know everything there is to know about h because we just have a few glimpses of it here. The key is recognizing that since h is differentiable, that means it's also continuous, which means that we can use the intermediate value theorem, the IVT, to at least guarantee a few values of 0 on this table. So let's look for places where we're changing h from negative to positive or vice versa. Because if we have a continuous function and you go from a negative to a positive or the other way, you're going to have to go through 0. So looking up here, I notice that 16 to negative 8, this is a sign change right here. So just writing this out kind of official IVT style, I notice that h of 6, which is negative 8, is less than 0, which is the number we're looking for, and that's less than 16, which happens to be h of 2. Therefore, because we have a continuous function and our value we're looking for sandwiched between these two outputs, that means that we are guaranteed that h of c equals 0 for some value on the interval from 2 to 6. So that guarantees at least one critical value then for f, because f prime is the same as h. Let's see if we can find another critical value. So as we keep going here, we're going negative to negative to negative to positive. So we have another sign change here somewhere between 9 and 11. So again, writing it out kind of official style, I notice that h of 9 is negative 5, which is less than 0, which is less than 7, which is the same as h of 11. This tells me that h of c has to equal 0 somewhere on the interval from 9 to 11. And that's the only other sign change in this table for h. So there's no other guaranteed places where h is going to be 0. But since h rather is the same as f prime, and since h equals 0 at least twice, that means f prime equals 0 at least twice, which means that f has at least 2 critical points on the interval from 2 to 13. So that's going to be choice C. On this problem, they just want us to take the derivative of this integral. Now, since this integral has an x in the upper limit of integration, using my fundamental theorem of calculus, all I have to do is replace the t's with this upper limit of integration. So this is just going to be x to the 4th plus x squared plus 1. And if we wanted to, we could multiply by the derivative of x, but that's just 1. So the chain rule here doesn't really do much for us. This is just going to be the final answer, so that's choice A. On this problem, I'm asking which of these is the antiderivative of cosine of x squared minus 5. So if you're trying to take the antiderivative of this thing, you're going to find it's pretty much impossible with the techniques you have. So our other option is to just look at these answer choices and see which of these I would have to take the derivative of to get cosine of x squared minus 5. And just kind of looking at doing the low-hanging fruit first here, these integral expressions would be pretty easy to take the derivative of just using my fundamental theorem of calculus. And between the two of these, this last one would be the easiest because we just have an x in the upper limit of integration instead of an x squared to mess around with. So if I just take the derivative of what I have in part D there, using my fundamental theorem, I'm just plugging this x in for the t. So this just comes out to cosine of x squared minus 5, which is exactly what we were looking for. Now, if you take the time to take all these other derivatives, you're going to find you run into one issue or another with a chain rule or a quotient rule. For this other integral expression, this would have been cosine of x squared minus 5 times the derivative of x squared 2x. So all these other ones end up having issues. Only choice D ends up working. So that's the answer. For this problem, they're asking for the antiderivative of tan of e to the x plus pi over 2. Now, if you're trying to just directly take the antiderivative of this thing, it can't be done, at least not using any technique that you know in either AB or BC calculus. Even the advanced integration techniques we learn in a calculus course are not enough on this one. So we go kind of to the fallback, which is, well, I have these answer choices. One of these, when I take its derivative, must come out to tan of e to the x plus pi over 2. And that's really the way you're going to have to do this one, is just take derivatives until you get what you're looking for. So the next question comes with, where should we start? Because there's a lot of different options we have here. We have 4 places we could start. We don't have to start with choice A. I mean, you could. If you start trying to take this derivative, you end up with, 2 times the secant of all this stuff times secant of this times tan of this. It's probably not going to come out to just tan of this, especially since you're going to have a chain rule going on inside with this e to the x that you're multiplying by. So that's probably not going to work. B just looks like a huge mess to take the derivative of. And in any case, you're going to end up with an e to the x squared in the denominator, because this is going to end up being a quotient rule. So this probably isn't going to work either. I mean, we could come back to it if nothing else works. For this one down here, choice C, well, now we're taking the derivative of an integral that has a variable in the upper limit of integration. So this is a little bit easier to do because you're just using your fundamental theorem of calculus. On this one, you would rewrite this as tan of e to the x plus pi over 2, because you're just replacing the dummy variable here with whatever's in that upper limit of integration. So that's good as far as it goes. The trouble is that you also have to multiply by the derivative of this upper limit of integration, which is an e to the x. So you end up with an extra e to the x if you try choice C. Now, if we try choice D, which I'm actually going to write down here, derivative of all this, you're just substituting x in for the t here. So this just gives you tan of e to the x plus pi over 2, and nothing else. And that's good, because we didn't want anything else. That's all we wanted. So we're going to pick choice D then. Why? Because it works. On this problem, I'm given this integral from negative pi over 4 to sine squared of x of all this craziness, and I want the derivative of this expression over here. Well, the good news is, since I'm taking the derivative of an integral with a variable in the upper limit of integration, I can just use my fundamental theorem and replace the dummy variable with whatever's in that upper limit, as long as I also use the chain rule when I do it. So I'm initially going to write, and this is kind of like the outer function in a chain rule, we're going to end up with cosecant of something to the 4th plus 1, the something in this case being this function sine squared of x. So this is cosecant of sine squared of x to the 4th plus 1. But now I have to multiply by the derivative of sine squared of x, which is going to be, let's see here, this is really something squared, so this is going to be 2 times sine of x, times the derivative of sine, which is cosine of x. And of course, this doesn't quite match any of the answer choices, so we need to clean it up just a little bit. I can move the 2 sine of x, cosine of x out in front if I wanted to, and inside this is really now going to be sine 8th power of x. And there isn't really too much more we can do to simplify here. The cosecant and the sine can't cancel, because this is sine of x and cosecant of, well, not x. So this just ends up being then, let's see here, answer choice D. For this free response problem, we're given the f and g functions. F is this integral from 0 to 3x of square root of 4 plus t squared dt, so an integral function. And g is just f of sine of x. For the first part here, they want us to figure out f prime of x and g prime of x. So for f prime of x, we're taking the derivative of an integral that has a variable in the upper limit. So using our fundamental theorem of calculus, we're basically just plugging this upper limit in for the dummy variable with and just getting rid of the integral. So we can initially write f prime of x equals square root of 4 plus 3x quantity squared times, since we're taking a derivative here, we have to use the chain rule, times the derivative of 3x, which is 3. And then if you really wanted to clean this up, which is not necessary, but you could do it, you can move that 3 out in front and write radical 4 plus 9x squared. All right, let's move on now to the g function. We want to take the derivative of that. But first, I'm going to write the g function out just to know what I'm actually taking the derivative of. So the g function just takes the f function and plugs sine of x into it. Well, here's the f function. So instead of writing all of this stuff with 3x, you could write all of this stuff with 3 times sine of x. So that's really the only difference between the g function and the f function. So I'm just going to use my fundamental theorem again. Now I'm going to have 4 plus 3 sine of x quantity squared. And I'm going to have to multiply now by the derivative of 3 sine of x, which is 3 cosine of x. And that's about as good as that one's going to get. For this problem part, I want the equation of the tangent line for g of x at x equals pi. So I'm going to use my point slope formula to plug things in eventually. But before I can do that, I need a point and a slope. So let's talk about the point first. I have the x value, pi. I need the y value that goes with that for the g function. So I essentially need to figure out g of pi. Okay, well, g of pi, I mean, here's the g function. It's f of sine of x. So g of pi is just going to be f of sine of pi. But wait a sec, sine of pi is just 0. So this is really f of 0. And here's the f function up here. So f of 0 is really integral from 0 to 3 times 0 of all that stuff. This looks like it's going to be kind of nasty, but here's the nice thing. 3 times 0 is just 0. The integral from 0 to 0, that since you have the same upper and lower limits of integration, this is essentially an empty integral. There's no area, so this just comes out to 0 automatically, regardless of anything else that's going on. So we've got 0 for the y value. We have the point pi comma 0. Now we need to figure out the slope. We need to figure out g prime of pi. So here was your g prime formula again from part A. We came up with that on our own. And I'm just going to plug pi in for x and all this stuff. So 3 cosine of pi times the square root of 4 plus 3 sine of pi quantity squared. Out here, 3 times cosine of pi, well, cosine of pi is -1, so this is really -3 out in front of the radical. And inside, we know that sine of pi is 0, so this whole term in here is getting zeroed out, and we're just multiplying -3 by the square root of 4, essentially. So this is really -3 times 2. I mean, you don't need to simplify it, but why not? So this just comes out to -6. All right, so here's point slope formula. You don't have to write it out, but I always like to write it just in case. So we've got y minus the y value 0 times or equals our slope of -6 times x minus the x value that they gave us here, pi. And that's it. No need to simplify. On this problem, kind of the final boss battle of this free response, they want us to write but not evaluate an integral expression representing the maximum value of g on the interval from 0 to pi, and then justify our answer. All right, so we know that if you were going to do the candidates test, we would have to consider g of 0 and g of pi, and also g of any critical values on here. So we're going to start by getting some critical values for g. So here again is g prime from part A, and doing a little analysis on this, we want to figure out where this thing is going to be 0. So 3 cosine of x is going to equal 0 wherever cosine equals 0. And on the interval from 0 to pi, the only place cosine is 0 on just that interval is going to be pi over 2. It's 0 in an infinite number of places, but that's the only one on the interval that they gave us. So that's the only one we have to consider. Now, how about this other factor? Because usually if you have two things being multiplied, you set each of them equal to 0. Well, this other factor, I mean, you're squaring the stuff inside here. So that automatically makes this either 0 or positive. and then you're taking that stuff that's either 0 or positive, and you're adding it to a positive number. So you're always going to be taking the square root of something that is at least 4, which means that this radical expression always, no matter what you plug in for x, will always, always, always give you a positive number. So there's no way it can ever give you 0, so there's no critical values that are going to come out of this part of it. So really, pi over 2 then is our only critical value. Okay, so at this point, you could use the candidates test, or you could try to anyway, and plug 0, pi, the endpoints, and pi over 2 into the g function and see which one gives you the maximum value. Here's the trouble with doing that. So, I mean, plugging in 0 and pi into g, which basically takes the sign of it and plugs it into the f function, that's not a huge issue with 0 and pi, because the sign of 0 and the sign of pi is just 0. And if you have a 3 times 0 up here, this is an empty integral and it comes out to 0. The trouble is, what do you do with pi over 2? I mean, sine of pi over 2 is going to be 1. So you would be doing 3 times 1, which is fine. But, I mean, how do you take the integral of this thing from 0 to 3? I mean, even if you know about integral evaluation theorem, you don't know how to take the antiderivative of this stuff. So this is going to be a big mess. A cleaner way of doing this, other than using the candidates test, would be to just do a little sign analysis and see, since this is the only critical value, if we can at least prove that this is a local max. Since it's the only critical value, that will also prove it's an absolute max. So let's set up a number line here. This is g prime that we're mapping out, and here's our critical value of pi over 2, and the endpoints 0 and pi. So doing a little sign analysis, between 0 and pi over 2, really that's all of quadrant 1. Now, taking a look at our g prime function here, we know that this radical part is always positive. So we don't really have to worry about that when we're doing sign analysis. It's all going to come down to the sign of 3 cosine of x, or really just cosine of x. If you take anything from quadrant 1 and plug it in for cosine, you're going to get a positive. And now between pi over 2 and pi, that's quadrant 2. If you take anything from quadrant 2 and plug it in for cosine, well, now your x values are negative, so cosine gives you a negative value back. Since we're changing from positive to negative at pi over 2, since g prime is positive from 0 to pi over 2, and g prime is negative from pi over 2 to pi, this proves that you have an absolute max at pi over 2. And again, the clincher here is that pi over 2 is your only critical value. So we haven't actually answered the question yet. They said, write an integral expression that represents the maximum value of g. So we have to kind of sort of plug pi over 2 into the g function. So doing that, our max is going to happen where g of pi over 2, well, at that value, that's going to be our y value. So that's really going to be 3 times the sine of pi over 2, because you're really doing sine of pi over 2 plugged into the f function. You could simplify this to integral from 0 to 3 of all that stuff if you wanted to. It's not necessary. Either of these answers, though, would be the integral that we're looking for.